Coming to the first question, fill in the blanks. First bit, the center of the circles lies in the circle, either exterior or interior. Now moving on to the solution for the first bit. We know that circle is a collection of all points in a plane which are at a fixed distance from a fixed point in a plane. Therefore, let us consider the figure of the circle that is shown in the figure. Here, the fixed point is known as center and the fixed distance is known as the radius. Therefore, center of the circle always lies in the interior of the circle. Now, coming to the second bit, a point whose distance from the center of circle is greater than radius lies in the edge of the circle, that is exterior, because if we consider a circle that is as shown in figure with center O, we know that radius is the distance between center and any point of the circle. Let us name the point as P. The distance between O and P is known as radius. If we consider the distance greater than R, then we can say that it always lies outside the circle. Let OR be the distance some R plus D, then it always lies outside the circle. Therefore, a point whose distance from the center of circle is greater than its radius always lies in the exterior of the circle. Moving on to first question, fill in the blanks. Now let us find the solution for third, fourth, fifth and sixth bits. Initially let us consider the third bit. For this he says that longest chord of circle is a dash of the circle. Let us consider a circle as shown in figure with center O. We know that longest chord of the circle is the diameter. Since if we draw a chord between any two points, that will be less than radius always. But if we draw any chord on the circle, the distance between 2 points on the circle other than the line passing through the center will have the length less than the diameter. Therefore, diameter is the longest chord of the circle. Now, moving on to the fourth bit. An arc is a when its ends are the ends of the diameter. Let us consider the figure as given. Let us name the points at the ends of the line passing through the center or the chord passing through the center as AB. Now, it divides the circle into two equal parts. Therefore, the arc formed by the chord passing through the center is nothing but the semicircle. Moving on to fifth bit. Segment of the circle is the region between arc and of the circle. We know that segment of the circle is a region between arc and the chord of the circle by the definition. Now moving on to the sixth bit. A circle divides plane on which it lies into three equal parts, because if we consider a circle, the points lying about the circle are of three types, that is, one is interior of the circle, other is the exterior of the circle, and some of the points lies on the circle. Therefore, circle divides the plane into three parts in which it lies. Moving on to second question. Write true or false, give reasons for your answers. Now moving on to the solution for the first bit. Line segment joining the center to any point on the circle is called as radius of the circle. That is true, because all the points of the circle are equidistant from the center, and that equal distance is known as radius. Now moving on to the second bit. A circle has only finitely number of equal chords. That is false, because for example, if we consider a circle, let us consider a chord that is passing through the center, which is nothing but diameter. As circle has an infinite number of points on it, we can draw a infinite number of chords passing through the center. Therefore, we can't say that there will be finite number of chords on the circle which are of equal length. Now moving on to the third bit. If a circle is divided into 3 equal arcs, each is a major arc. That is false, because if we consider a circle, it is divided into 3 equal arcs, that is AB, BC and CA. If we consider AB as the arc, then other arc, that is ACB, will be the major arc, but AB, AC and CB can't be the major arcs individually. Moving on to second question. Write true or false. Give reasons for your answers. Now moving on to the solution for the fourth bit. A chord of the circle which is twice as long as radius is called as diameter of the circle. That is true, because we know that chord which is passing through the center of the circle will be having the length as 2 times the radius. Therefore, that will be the diameter of the circle. Now moving on to the fifth question. Sector is a region between chord and its corresponding arc. That is false, because segment is nothing but the region between chord and the either of its arcs, but it is not the region between the chord and its corresponding arc. If we consider a circle and let us consider a chord AB, then the region between AB and the arc is called as minor segment, and other remaining part is known as major segment. Now moving on to the sixth bit. A circle is a plane figure. It is true, because by the virtue of definition we can say that a collection of all points in a plane which are at a fixed distance from fixed point in a plane is called a circle. Moving on to question number 1. Recall that two circles are congruent if they have the same radii. Prove that equal chords of congruent circles subtend equal angles at their centers. Now moving on to the solution. Let us consider two congruent circles as shown in figure. Let the center of one congruent figure be O and other congruent figure be O dash. We know that the radii of two circles will be equal. Let us consider two chords AB and CD of equal lengths in two circles. Let us draw them, that is AB and CD, both are of equal lengths. Now we need to prove that angle subtended by them at the center must be equal. That is angle AOB is equal to angle CO dash D we need to prove. In order to prove this, let us consider in both triangles, that is triangle AOB and triangle CO dash D, OA is equal to O dash C. Since the figures are congruent, their radii will be equal, and OB is equal to O dash D. Since the figures are congruent, their radii will be equal, and also initially he has given that chords are of equal lengths, therefore AB is equal to CD. Now by S.S property of congruency we can say both the triangles are congruent. That is, triangle AOB is congruent to triangle CO dash D. When two triangles are congruent, then their corresponding angles are equal. Therefore, angle AOB is equal to angle CO dash D. Therefore, equal chords of congruent circles subtend equal angles at their centers. That is proved. Moving on to question number 2. Prove that if chords of congruent circles subtend equal angles at their centers, then the chords are of equal length. Now moving on to the solution. Now in the solution, let us consider two circles respectively with the centers O and O dash, and AB and PQ be the equal chords Let AB and PQ be the chords in the two congruent circles which subtend the equal angles at the center, that is angle AOB is equal to angle PO'Q. Therefore, let us note down the information that there are two congruent circles given with centers O and O dash, and he has also given angles subtended by the chords at the center is of equal. Therefore, here we can say that angle AOB is equal to angle PO''Q. We need to prove that AB is equal to PQ. In order to prove this, let us consider in triangle AOB and triangle PO''Q, OA is equal to PO'. Since both the circles are congruent, we can say the radii will be equal, and OB is equal to O''Q. They are also the radii of the circles, and he has given that angle AOB is equal to angle PO''Q. Now hereby S.A.S property of congruency, we can say triangle AOB is congruent to triangle PO''Q. Therefore, we know that when two triangles are congruent, then their corresponding sides and corresponding angles can be equated. Therefore, here we can equate AB is equal to PQ. Now, the chords which subtend the equal angles at the center are of equal lengths is proved. Coming to the first question, draw different pairs of circles. How many points does each pair have in common? What is the maximum number of common points? Now, moving on to the solution. Let us draw the different pair of circles. Firstly, let us consider the pair of circles which doesn't have any common point. The below figure represents the two circles respectively with the centers O and O', and they doesn't have any point of intersection in common. Secondly, here let us consider a pair of circles. They having one point in common, that is shown in the below figure, that is circle respectively with center O and O' having only single point in contact. Now let us consider the third pair of circles. Now let us consider another pair of circles, that is as shown in figure respectively with center O and O'. These have 2 points of intersections, that is they have 2 points in common. There is no possibility for another pair of circles to be existed that are to be intersecting in 3 points or 4 points. Therefore, we can say that a pair of circles can have maximum 2 points in common. Moving on to third question. If two circles intersect at 2 points, prove that their centers lie on the perpendicular bisector of the common chord. Now moving on to the solution. Let us consider two circles as shown in figure. Let their centers be O and O', and they intersect at the common points AB, and now AB will be their common chord. We need to prove that O' is perpendicular to AB. Let us assume that O' intersect AB at M, and AM is equal to MB. Now moving on to the solution. We have considered two circles with centers O and O', and AB is a common chord for both the circles. We need to prove that line joining centers, that is O' is perpendicular bisector of AB, or AB is perpendicular bisector of O'. Now moving on to the solution. Let us join AO, BO, AO' and BO'. Let us consider triangle OAO' and triangle OBO dash. In these two triangles, OA is equal to OB since they are the radius of the smaller circle with center O, and O dash A is equal to O dash B since they are the radii of the larger circle with the center O dash, and O dash is equal to O dash, which is the common side for both the circles. Therefore, hereby as triplets property of congruency, we can say both the triangles are congruent. That is, triangle OAO dash is congruent to triangle OBO dash. We know that when two triangles are congruent, then their respective sides and corresponding angles can be equated. Therefore, here we can equate angle AOO dash is equal to angle BOO dash. Now, let us consider other two set of triangles, that is triangle AOM and triangle BOM. In these two triangles, angle AOO dash is nothing but AOM is equal to angle BOO dash is nothing but angle BOM, since we proved in the above, and OM is equal to OM since it is a common side, and also OA is equal to OB since it is the radii of the circle with center O. Therefore, by S.A.S property, we can say both the triangles are congruent. That is, triangle AOM is congruent to triangle BOM. When two triangles are congruent, then their corresponding sides and corresponding angles can be equated. Therefore, here AM is equal to BM, and we can equate a pair of angles, that is angle AMO is equal to angle BMO. But angle AMO and BMO form the linear pair. Therefore, sum of them, that is angle AMO plus angle BMO, will be equal to 180 degrees since they form the linear pair. Let them be equal to some x degrees. Then we get here angle AMO is nothing but x degrees plus angle BMO is nothing but x degrees, that is equal to 180 degrees, which implies 2x degrees is equal to 180 degrees. That further implies that x is equal to 180 degrees by 2, that is nothing but 90 degrees. Therefore, here we got angle AMO is equal to angle BMO is equal to 90 degrees, and we also got that AM is equal to BM. Therefore, OO dash is perpendicular bisector of AB, and the relation is mutual, so we can say that AB is also perpendicular bisector of OO dash. This is what the required proof for us. Coming to the question number 1. Two circles of radii 5 cm and 3 cm intersect at 2 points, and the distance between their centers is 4 cm. Find the length of common chord. Now moving on to the solution. Let us consider two circles intersecting at 2 points. Let us consider two circles as shown in figure which are intersecting at 2 points. Let those points be A and B. Let centers of circles be O and O dash. Here he has given the distance between their centers, that is O dash is equal to 4 centimeters. And the radius is given as 5 centimeters and 3 centimeters of each circle respectively, that is OA will be equal to 5 centimeters, OA will be equal to 5 centimeters, and OA dash will be equal to 3 centimeters. Let us join OA and O dash A. Now OA square is equal to 5 square, which is nothing but 25, and also O dash square plus O dash A square is nothing but 3 square plus 4 square, that is 25. Therefore here O dash A is a right triangle. Therefore we can say that O dash is right angle triangle. And now let us join AB, that will be the common chord. We know that the line joining centers of circles perpendicularly bisects the common chord of the two circles. Therefore we can say that O dash will be perpendicular to AB, and the length of the chord will be equal to 2 times the line joining centers, that is equal to 2 times O dash is nothing but 4 centimeters. Therefore we get AB is equal to 8 centimeters, that is length of common chord is equal to 8 centimeters. Coming to the second question, if two equal chords of circle intersect within the circle, prove that segments of chord are equal to corresponding segments of other chord. Now moving on to the solution, let us consider a circle as shown in figure. Let the circle be with the center O, and here AB and CD be chords of equal length that intersect at point M. Therefore here in the solution, AB and CD are chords such that AB is equal to CD, and here AB and CD will intersect at point M. Now let us draw a perpendicular OE to the chord AB and perpendicular OF to the chord CD. That is, we have drawn here OE perpendicular to AB and OF perpendicular to CD. Let us join OM. Now here, if we observe in triangle OME and triangle OMF, angle OEM is equal to angle OFM is equal to 90 degrees, since we have drawn the perpendiculars, and OM is equal to OM, which will be the common side for both triangles, and the perpendiculars drawn from center to the equal chords will be of equal lengths. Therefore we can say that OE is equal to OF. Therefore here by property of R.H.S. congruency, we can say that both the triangles are congruent. That is, triangle OME is congruent to triangle OMF. Here we got that two triangles are congruent. Therefore we know that when two triangles are congruent, then their corresponding sides can be equated. Here let us equate the corresponding sides, that is ME is equal to MF. That implies instead of ME we can write EB minus MB or BM. That is equal to, instead of MF we can write here DF minus MD. But we know that the lines perpendicular to the chords from the center always bisect the chord. Therefore we can say that EB is equal to half AB and DF is equal to half CD. Let us substitute in the above equation, then we get half AB minus BM is equal to half CD minus MD. But we know that AB is equal to CD since we have taken the equal chords. Therefore half AB will be cancelled on both sides. We are left with minus BM is equal to minus MD, which implies BM is equal to MD. This is the First thing, that half of the segments from the intersection point are equal. Next we need to prove that other segments, that is AM is equal to CM. In order to do this, let us consider that EM is equal to MF. That implies, let us add half AB on both sides. Then we get half AB plus EM is equal to MF plus half AB. That implies half AB plus EM is equal to MF plus half AB can be written as CD. That implies, here instead of half AB we can write the value as AE, since AE is equal to half AB plus EM is equal to MF plus half CD can be written as FC. Therefore, now again from figure we get AE plus EM is equal to AM and MF plus FC is CM. Therefore, here we got AM is equal to CM. Now, by the result 1 and 2, we can say that if the two equal chords of a circle intersect within the circle, the segments of one chord will be equal to corresponding segments of other chord. Moving on to question number 3. If two equal chords of circle intersect within the circle, prove that the line joining point of intersection to the center makes equal angles with the chords. Now moving on to the solution. Let us consider a circle with two equal chords in it. So in the solution we have considered a circle with center O and two equal chords, that is AB and CD, of equal lengths intersecting at point E. Therefore, here given that AB and CD are two equal chords, and here, so we can write that AB is equal to CD. We are required to prove that line joining the point of intersection, that is E, to the center divides equal angles with the chords, that is angle OEC must be equal to angle OEA. This we need to prove. Now, in order to prove that, let us draw perpendicular OP to the AB chord and perpendicular OQ to the CD chord. Therefore, here we have drawn OP perpendicular to AB and OQ perpendicular to CD. Now, let us consider in both the triangles, that is triangle OEP and triangle OEQ. Now let us consider in triangles OEP and in triangle OUQ, angle OPE is equal to angle OQE is equal to 90 degrees, and here OE is equal to OE, since it is a common side and also hypotenuse, and we know that chords of equal length or equal distance from the center, we can say here OP is equal to OQ. Therefore, by R.H.S property of congruency, since it is a right angle triangle, we can say both the triangles are congruent. Therefore, triangle OEP is congruent to triangle OEQ. We know that when two triangles are congruent, then their corresponding angles and corresponding sides will be equal. So here we can equate angle OEP is equal to angle OEQ. This is what the required proof for us. That implies this can be further written as angle OEA is equal to angle OEC. So this is what the required proof for us, and it is hence proved. Moving on to question number 4. If a line intersects two concentric circles, that is circles with same center, with center O at A, B, C and D, prove that AB is equal to CD. Now moving on to the solution. Here he has given that there are two concentric circles with the same center O, and A, B, C and D are the points lying on them as shown in figure. Now he asks us to prove that AB is equal to CD. Therefore here we are required to prove that AB is equal to CD. In order to do this, firstly draw OM perpendicular to AD. Now in the first concentric circle, let us consider that OM is perpendicular to BC. Then we know that the line from center to chord drawn perpendicularly bisects the chord. Therefore here we can say that BM is equal to MC. Let it be as equation number 1. Similarly, if we consider that OM is perpendicular to AD, then we can say that OM is perpendicular to AD and it divides the segment AD into two equal halves, that is AM is equal to MD. Let it be as equation number 2. Now let us consider 2 minus 1, which implies AM minus BM is equal to MD minus MC. That implies AM minus BM is nothing but the segment AB is equal to MD minus MC is nothing but the segment CD. Therefore this is what the required proof for us, that is AB is equal to CD, and it is hence proved.